So, last class we have solved a problem, that is we have to optimize a functional, agree, we have to optimize a functional without any constraint, that means unconstrained optimization problem. We have seen how to solve using calculus of variation technique. Then we have considered the application of calculus of variation to control problems. If and we could not complete that whole exercise. So, let us recollect what we have discussed last class. Consider a dynamic system described by x dot is equal to f, which is a function of the variable state and the control input to the system u t and time. So, this may be a linear function, may be a nonlinear function, which we did it that a dynamic system which can be described by a nth order differential equation, that dynamic equation is converted into a n first order differential equation, and they are coupled each other, and that differential equation may be linear or nonlinear. So, our problem is to optimize this performing index. What is this performing index? One term of the performing index is the functional integral integral of the functional, and another is a fixed measure is terminal cost. That means, x time t is equal to t f, this state is x t f is known and t is equal to t f, that terminal cost is given. So, you have to optimize this performing index in order to find out u of t control input such that performing index is minimized and it as well as it satisfies the dynamic equation. So, the control input will dictate the response of what is called state. So, we have a performing index, this is index I n, omitted I. So, I n index. So, this is the system, input is there, we have to design that input such that the performing index is minimized in our case, in the sense that this is the integral part of the performing index and is the fixed part of the performing index, which is the terminal t is equal to t f, this terminal cost is known to us. Agree? So, our objective is now that if you see u of t, you find out u of t that minimizes the performing index, that why what we have considered subject to the constraint 1, subject to the constraint 1, that our constant is that dynamic equation, this dynamic equation is the constant. So, this is a what is called constraint optimization problem. Previously, we have discussed the minimization of a functional without any constraints, but here now we are considering the constraints, and this problem is also known as Boltzmann problems. So, what we did it that terminal cost, what is the terminal cost, that we like to push it in the integrand part of this performing index. So, this terminal cost, that d f s dt we can write it in this. So, this terminal cost, this is the terminal cost. The terminal cost will be expressed in terms of integral and that constant term, because t is equal to 0 and the terminal cost is fixed known. So, using this equation in our original performing index, that we get it this one, agree, just you put it the terminal cost expression in terms of this and this, that what we have seen earlier slide. So, our problem minimization of performing index 2, minimization of performing index 2, that one, minimization of performance 2, this one, that performing index 2, this is because we have replaced this thing in terms of integral part and constant part, is same as minimization of the performing index 4, subject to the constant x dot is equal to f of x, that constant. So, up to this we have discussed last class. So, now this is the constant term. So, minimization of 4 is equivalent to minimization of this integral part of that one is same, because constant term, what is this minimization of that one, at what point, or what trajectory of u t this function will be minimum with constant term also at that value of u star or trajectory the function will be minimized. So, instead of equation 4 we can rewrite the equation 4, the you can write it optimization of equation 4 is equivalent to that of j is equal to this integration of t 0 to, I am writing same expression except that constant term x of t u of t t dt plus t 0 to t f ds x of t, which is a function of x and t s terminal cost into dt. So, minimization of that function is same as the minimization of this objective function. So, before that further derivation we just recollect what is called chain rule in differentiation. So, let us call we have a function f which is a function of x t, x is a function of x t, y also function of time parameter time t and z of t. Agree? We want to differentiate this with respect to time t. Differentiation of this with t, this is the by chain rule del f del x into x dot dx dt x dot of t plus del f del y y dot of t plus del f del z z dot of t. Z is a function of time. So, we differentiate this z with respect to time t z dot t. So, this chain rule I will apply here to find out this one. So, say what once again can f is a function of x, y, z and x is a function of time t, y is a function of time t. So, differentiation of x with respect to t is nothing but a partial differentiation of f with respect to x, because it is a function of x, y, z. Keeping y, z constant you differentiate this one and then differentiation of x with respect to t. Differentiation of x with respect to y keeping x and z constant then multiplied by y dot. Similarly, differentiation of x with respect to z keeping x y constant then multiplied by z. So, this chain rule I apply here, because it is a s is a function of time x t and t. Agree? So, this I can write it then j is equal to j dot of this t 0 to t f, then v as it is we write as it is this term, we will write as it is this term x of t, this is capital x of t u of t t dt, and this we will write it by using chain rule. So, this will be a plus t 0 to t f. So, what we will write it differentiation of ds dt differentiation with respect to time t, because s is a function of x t and t. So, what we will write it that one, that will write del f del s with respect to x of t into that x dot of t, x dot of t, this is capital X, plus del f del s of this with respect to dt and t differentiate with respect to time t. So, that means it is 1, that whole thing into dt. So, for this portion we have written that one. So, now see what we can simplify that one. This expression, if you consider this is equation number 6, agree, this performing index, that means equation 4, minimization of equation 4 is equivalent to minimization of equation 5, because in equation 4 there is a constant term is there. Agree? So, optimize at what value of u you will get the maximum or minimum value of the objective function without considering what is without considering the constant term, I will get the same stationary point mean u star of t to optimize this functional. Agree? So, equivalent, it is equivalent to say the optimization of objective function 4 is equivalent to what is called optimization of objective function 5, subject to constraint, same constraint what we can x dot is equal to f x of t u of t comma t. So, this equation, this by using chain rule we have written this subject to our same constraint, subject to x dot of t is equal to f x of t u of t of this is the subject. So, this is a what is called constraint optimization problems. We know very well how to, in static optimization problems also we have seen how to convert a constraint optimization problem to a unconstrained optimization problem. And then what we have discussed in calculus of variation is our first problem, that if you have a functional what is called j, which is a integrand part is v of x t comma x dot of t comma t dt, then we know how to optimize that function. So, first our job is convert this problem what is called constraint optimization problem to a unconstrained optimization problem. Our problem is find u such that, find optimum trajectory of u such that this performing index or objective function is minimized subject to these constraints, and that constraint is a dynamic equation. So, that let us call this is equation number 2. So, our job is convert equation 6 and 7 into unconstrained optimization problem using Lagrange multiplier. So, that is what we have discussed earlier, that way we can do it. Next is what is our modified performing index. When you use the concept of Lagrangian multiplier, what is the our modified performing index. So, our j is equal to T 0 to T f v x of t u of t t dt plus integration of del s back a function of time x t, this del x of t whole transpose. See this one, that part I am writing, but here you see if you consider x is a, if you consider x is a vector of dimension n cross 1, then you have to, it will be a row vector multiplied by column vector, then it is a scalar quantity, the whole thing is a scalar quantity. Agree? So, this you have to take transpose, agree? Transpose that one. So, that will be transpose into x dot of t plus del s x of t t del t, this one, and this whole is dt. Just this equation, this and this I clubbed together, I am written in that one, this plus, because it is a unconstrained optimization problem, because constant optimization problem now I have converted it into unconstrained optimization problems. Agree? So, Lagrange multiplier is used, and that dimension is, if the dimension of x is n cross n, that dimension will be n cross n, and that must be a column, a row vector, because the product of this must be a scalar one. So, that is equal to f of x, the dynamic equation, the constant equation, you can say this is t bracket, this is t bracket minus x dot of t, and this part is 0. So, I multiplied by constant, what is called our Lagrange multiplier. This is the Lagrange multiplier, lambda is Lagrange player. So, this is the equation number. I can write the whole thing. If you write it, this whole thing, I can write that is okay. This bracket, this whole thing you bracket it, complete it here, and dt. So, now see this performance index of that one is same as before, because this part is 0 when it is optimize the function of, that is our objective function. This part will be, because it must satisfy the our constraint, it must be 0, that one. So, this I have just written it. So, that is equivalent to T 0 to T f, T 0, this is T f, T 0 to T f, that I use the another function name is Lagrange function. So, that is the function of, if you see x t, u t, then lambda t and t whole into dt, that whole this plus this plus this plus this whole I am denoted by L. So, this is, this L is called Lagrange function. So, let us call this equation number is 8. So, now you see it is now, it is our original problem what we have considered, we have to optimize a functional, agree, without any constraint. Now, it is becoming same problem. So, we can apply the same technique what we have discussed earlier to find the optimal value of the functional subject, there is no constraint, agree. So, what is the necessary condition, what is the sufficient condition, we can easily derive. So, for your convenience I just will derive this one, because L function now is different from V. So, let us see this one where L, which is a function of x of t, u of t, lambda of t and t, which equal to V, the integrand part of that equation 8 I am writing. So, that is equal to V function of x of t, u of t, lambda of t and t, okay, plus if you see this one plus lambda this transpose, then f of x of t, u of t, then t, agree. So, what I did it here, this term integrand part, this term and only this part, I mean not considering this and this part, I have written together this plus the remaining term. So, what is the remaining term is del s del x of t del x of t, this whole transpose into x dot of t plus del s, which is a function of x t of t differentiation with respect to time t, minus lambda transpose x dot of t. So, this is the things. So, this and this, that means which is a V and that lambda transpose of x transpose t, agree. This we denoted by a function x h, which is a function of lambda x u t and lambda t and t. See this one. That means, if you just consider the integrand point of the objective function, that plus the constraint, what is x dot is equal to f x, f that constant right hand side of the constraint multiplied by a vector, agree, that term I am considering a function which is denoted by h, and that h is called Hamiltonian function. We will see, if you split up this Lagrangian function into this form, that will be convenient when we apply to our control problems, agree, and that control problem description when it is given into a state space form. It will be convenient when you will express this thing into a Hamiltonian form. And what is the leftover terms? This. So, del s x of t of this del x of t whole transpose x dot of t plus del s x of t del t minus lambda transpose x dot of t. So, this is the so Lagrangian equation is nothing but a Hamiltonian function plus some of the differentiation of s terminal cost with respect to x transpose x dot plus differentiation of terminal cost this with dt and then minus lambda transpose into x dot is that one is expressed in this one. So, once you do this one, then I can write now this perturb at perturb condition, what is the value of J at the perturb condition. Perturb condition means, if you see this sequence, that J is defined this one, when x is perturbed with a x t plus delta x t, u t perturbed with a u t plus delta t, agree, and t is that one, t is equal to t. So, this trajectory, what does it mean? Our job, if you see this one, we have to look for a optimal trajectory of u star, agree, which in turn this performing index will be minimized subject to this constraint. So, let us call whatever the u star is there, u is the optimal trajectory around this u, around this optimal trajectory u, there is a neighborhood of u, there is another trajectory, agree, and that trajectory, if you consider that trajectory, what is the and corresponding functional value of the objective function will be what corresponding to that perturbed trajectory. When u is perturbed by u t of delta u of t, similarly with the control action of this one, x will be also perturbed. So, I am writing this one now t 0 to t f, and that time t, final time is t, it is perturbed with a delta t f, agree, then v, and if x star is the optimal trajectory and we have given the perturbation of delta x t, similarly u star is this and perturbed with u star of t. U star is the optimal trajectory and it is perturbed from the neighborhood of u star is delta u. So, which in turn x also will change from optimal trajectory x star to delta x t, and this t plus delta s of this delta x whole transpose that and x dot, because if you see this one, this is the value of this one, you find out this value of that one, differentiate with respect to this along the trajectory of this one. So, this star plus x dot star plus delta x dot of t. This is the that part we have written, part of trajectory of that one. Then what is left? The del s of del t whole star is there, just that one plus this term plus lambda of t transpose then f x star of t delta x t plus u of t u star of t plus delta u of t then t. Agree? Minus x dot minus this f of x I am written, this minus x dot is, what is x dot? X dot star of t plus delta x dot of t. So, this of integration dt. So, what I did it this, suppose j is the value of the functional value. Now, I perturb u by u plus delta u, naturally x will be part of x plus delta u, agree, and then we are finding out here what is the new objective functions when we perturb the trajectory u star to u star plus delta u and x star to x star plus delta u. So, this and that are integration in t 0 to t delta t f, because our final time also that is changed to t f to delta t f. So, now this is the objective function value. What is the incremental of incremental functional value? So, one can find out this is nothing but a, if you see this is nothing but a, I can write it t 0 to t f L p means perturb model, perturb functional L p dot of t dt. This whole thing is perturb, p stands for perturb, the whole thing is this. So, this I can write it equal to, this is delta t f, mind it, agree. Now, whole thing I just can write it this, that t 0 to t f L p dot dt plus t f to t f plus delta t f L p dt. So, it is a perturb Lagrange function, this L p. So, this I can write it nearly equal to, if you this think of it, this is as it is t 0 to t f L p dot this dt, and this is nothing but a L p is a functional scalar functional, and area under this curve from t f to t f plus delta f. If you just consider just like this way, it is the trajectory from this is the t f, agree, and this is the your t f plus delta t f, and this is our L p dot function, agree. This is the L p I am plotting this function. Now, what is the area under this curve? T f to T f is nothing but a this whole thing, agree. So, one can write this is nearly equal to, find the ordinate of the Lagrangian function value at t is equal to T f. So, find L p, this is L p, what is called, if you see this is L p and there is a another curve is that one. What is this one? This is L dot this, t is equal to T f this, and this is the t is equal to that is T f to T f plus delta T f. This is without part of Lagrangian function, without part of Lagrangian function. So, area actually I have to find out the area from here to here with a part of molar is same as, I can write it is same as the area, find out the function of the Lagrangian function value at t is equal to T f, this function, that means this ordinate you find out, multiplied by delta T f. So, this will be approximately, because delta T f very close to T f. So, I can write the area under this curve is same nearly equal to area under the L p from T j f to T f plus delta f, T f plus delta f, agree, that we can write it. So, that is why I am writing nearly equal to that one. So, if it is so, then I can, what is the variation of functional value? Variation of functional value delta j a, the variation of functional value j a dot minus j dot is nothing but a T 0 to T f plus delta T f, agree, L p part of function Lagrangian function value, this one j minus T 0 to T f, that original Lagrangian function without perturbation, this one, this we have written. So, that just now we have concluded this part, we can write it T 0 to T f L p dot d t, and that is nearly equal to, I can write it nearly equal to L dot value the find the value the value of the Lagrangian function t is equal to T f into delta T f minus T 0 to T f L dot delta t. So, you club this and this club together. So, this nearly equal to T 0 to T f L p dot minus L dot this d t plus L dot t is equal to T f delta T f, agree. So, this we got it, that one. Now, one can write it this this is now as before we have discussed this one, agree. Now, what we can write it for this one, this nearly equal to, if you write more details T 0 to T f, L p is what? V, L p is that L p function I am writing, what is the function of L p is equal to x dot t plus delta x of t u star of t plus delta u of t, again is a function of this and lambda of t minus that one I am writing, that is minus L function of x star of t u star of t lambda of t of this whole bracket d t. That this part in details I have written is a function of part of input and part of output, again that we have written, and then left remaining term is that one plus L x star of t u star of t lambda of t bracket close, find the value t is equal to at T f multiplied by delta T f. So, let us call this equation number is, we have given equation number up to 8. So, now this equation is equation number 9. Now, see this one, this part, if you do the Taylor series expansion, then use the what is called chain rule, all these thing as we did in earlier, we can simplify this to first part of the integrand of that one, we can simplify, and how, what is the final expression will come using, I am just writing it, using Taylor series expansion and integration by parts rule, we obtain. I do not want to repeat this one, because this we have already discussed when we have considered the functional j is equal to 0 to t 0 to t f v function of x t comma x dot t comma t dt. When we are deriving that of what is the necessary condition for the functional to be optimized, there we have used that operation. Please refer that derivations, then you will get it Euler's equations. So, and if you take the first variation of that one, if you take the first variation of this, if you do the Taylor series expansion and take the first variation of the functional, then you will get del j is the first variation of the functional, first variation of the functional, that equal to, if you do the Taylor series expansion and use the what is called integration by parts and simplify, then ultimately you will get the first variation. This is the, this delta j is the variation of the functional, variation of the functional. Okay. Means when t 0 to t f plus delta t f and part of states inputs are part of x, in turn x also part of, that is denoted by j minus without part of Lagrangian integrand of the that Lagrangian function. Difference is first, that is variation of functional. Out of this we split up into two parts, that first variation of the functional, second variation of functional is there, third variation of functional is there, and so on. So, we are just considering the first variation of functional for the necessary condition for the functional to be optimized. So, let us see that one, what is the functional variation after simplification. It will be t 0 to t f del L dot del x of t, agree, minus d of dt del L dot del x dot of t. So, this you compute at optimal trajectory, this whole transpose delta x t dt plus some of the terms are remaining terms are like this, del L del u, because you will, it will come from the what is called Taylor series expansion in first order terms, agree. So, this star transpose del u of t. So, u is a vector of dimension m inputs. If you consider u is a vector of dimension m inputs, in the beginning if you see what we have considered, that one, here if you just, no, not this one, here if you could say consider the our original function x of t u t, x u is the number of inputs, that m cross 1, x is the n cross 1, agree. So, the partial derivative of L with respect to u, if L is a scalar thing, u is a vector of m cross 1. So, this will be a vector. So, you have to transpose multiplied by delta, then you will get a scalar quantity that. So, this plus del x dot of t whole transpose star delta x of t agree, and that is T is equal to T f. That is, we have derived this by substitution, Taylor series expansion and substitution, you will get this expression. Then now see, you consider our that popular lemma that we considered, that lemma is 0 to T 0 to T f. I am repeating this one once again. You have a g of t, then delta x of t dt is equal to 0. So, g of t is a continuous function and it is differentiable each and every point in the interval this, and delta x is the small change in that variable small element. If we integrate with respect to time t, that value will be 0, provided if and only if g of t is equal to 0 at every point over the interval, at every point over the interval T 0 to T f. So, if you consider this equation number is 10, okay, 9 we have done. If you consider this is equation number 10, then using this lemma I can write this quantity will be 0 provided that this quantity is 0, because delta x is not equal to 0, this equal to 0. So, our necessary condition just as before we did it, that this del L del x of t minus d of dt del L dot del function of this del x dot capital X dot of t whole this is equal to 0. And what is the dimension of this one? L is a scalar, I am differentiating with respect to n, with respect to x, whose dimension in n cross 1. So, this dimension will be n cross 1. So, this star indicates that if you solve the differential equation, agree, for that one you may need some other boundary condition. Let us call, if you solve this one, then whatever the trajectory you will get it, that is the optimal trajectory. The star indicates the optimal trajectory of this one. So, let us call this equation is equation number 11. So, this part is 0. Now, you see, when you have made an increment u star to delta u this is not equal to 0, this is not equal to 0, and this is independent of, this is the, you can write independent contour variable. Okay. So, this is not equal to this part. So, this must be equal to 0 in order to make that. Agree, our dt is there here. If you see the last equation, there will be a dt is here, agree, dt here, missed this one. So, this equal to will be 0. So, next condition is del L dot del u of t, that compute along the trajectory. If you do it, this will be a 0 whose dimension is m cross 1, because u's dimension is m cross 1, I am differentiating with respect to scalar quantity. So, that will be m cross 1. Let us call this equation is equation number 12. So, we have a, you see, when we have a two necessary condition, this and this necessary condition you got. So, this is 0, this is 0, only the term is left with you, with us is that one, another term is left here, because I have just another term is left here, the plus, please correct it, plus L dot star L dot star T is equal to T f. Find out the L dot star by T f into delta T f. This is that term. If you recollect that one, we did it, that is this term. This term, because this we have done a Taylor series expansion, that one Taylor series expansion of that one, and that term is this one. That term we missed it here. So, this. So, first term, second term and third term, what we got it due to the Taylor series expansion of this and this, we got it up to this. Agree? Then what is the leftover term is there. So, our when you use the lemma this and this, then we got it that what is called this equal to 0 and that equal to del L with respect to U 2 transpose, that will be 0. That two necessary condition. In addition to that, still delta j, first variation of the function is not 0. What is the finally left over with delta j? Finally, we left over with delta j is equal to nearly equal to, you can say that delta L dot star put L dot star, or you can star, you give it here, T is equal to T f into delta T f plus del L dot del x dot whole star delta x t, T is equal to T f. That means, x T f means x is equal to, this is x T f, T is equal to T f. Agree? So, that value is, I can write it now, this, if you see this one, our figure, let us go back to our figure, the optimal trajectory of this one. This is our A, this is our B, this is our D, and this is our C. So, this is our, let us call T 0, and this is our T f, and this is our T f plus delta T f, agree, and this value is, this value if you consider, this value is, and this value, and that we have considered delta x T f, and this value we have considered delta x f, as we discussed earlier. So, we can write it delta x f, that means from this to this point, that may coordinate of C and this distance of that one is delta x f is equal to delta x T f plus x a dot, this is x capital X a dot, this is our x a of t, this is our x star of t, which is equal to x star of t plus delta x of t. Agree? I just find out the slope at this point. So, this is nothing but this slope is x dot type t is equal to T f multiplied by delta T f. This I can write it. That means, this height plus this tangent at this one multiplied by this height is equal to delta x T f. So, this I can write it delta x T f plus, what is this one, I can write it delta a dot of this delta x dot, we can write it delta x dot is equal to x dot star t plus delta x dot t whole, t is equal to T f delta T f. Now, see, this is a small quantity, very small quantity, this is also small quantity, the product of this is you can neglect it. So, we can write it the nearly equal to this, we can write it delta x T f is equal to x dot star T f into delta T f. This product is third term, you neglect this one. So, this we can write it. So, now equation what we got it, equation 12, and then and let us call this is equation number, that is equation number 13. You consider the equation number of 13 is that one. Agree? So, now use this value x T f, x delta x t is equal to T f, delta x T f I can use the value from here. Agree? Using you can write it from 13 using this expression, that means I will write x delta T f is equal to x f minus of that one. So, what we can write it from 13, delta j is equal to L dot this star T is equal to T f and delta T f plus this one delta L dot x dot of T whole transpose star T is equal to T f. Now, I am writing x delta T f, this is x delta T f, value is delta x f minus x dot star T f into delta T f. Agree? This equal to that, this is I am writing is that quantity. In place of delta x T f I am writing is that quantity, if you see that one just like it is. So, this equal to we got it. Agree? Now, you see what we can write it delta T f if you consider together, then what we can write it, see simplifying that equation. If you simplify this equation, I can write it or delta j is equal to L dot minus del dot del x dot of T whole transpose x dot of T that whole star, agree, the whole star, then put T is equal to T f, just I am writing that one, this term plus this term into this term I am writing T is equal to T f. So, first is star I am writing it here, you calculate the star, then T is equal to T f, then what is left delta T f plus what is left, only this term is left, this term, this and this term is left. So, that is I am writing is del L del x dot of T whole transpose star T is equal to T f is equal to delta x f. See, this is delta x f, delta x f. Now, in order to become this is 0, that means what is the condition? That delta j first variation, our necessary condition is, if you see the basic necessary condition, delta j must be 0. So, in order to make the necessary condition, we got it two condition. In addition to the two, the third condition is that L this minus del L del x dot of T whole transpose x dot of T this agree, star evaluate t is equal to T f delta T f plus delta dot delta x dot of t whole transpose star t is equal to T f delta x f is equal to 0. That means, j is equal to 0. So, our first variation, in order to become first variation of this one, this part is 0, this is one necessary condition, and that part is 0, this second condition, and third part is what is called that we got it, that must be 0, and that depends on the our condition. Let us call our final time is fixed, T f is fixed, then T f is fixed means delta T f is 0, delta T f is 0. So, this is automatically 0. So, only an x T f is free, that means, delta x f is not equal to 0, it must, in order to make 0, this must be 0, agree. So, in other words, you can say in other way you can say, if T f is free and delta x f is fixed, agree, this is 0. So, this part will be 0 and T f is free, mean delta T f is not 0. So, this must be 0 in order to make this is 0. So, let us call this equation number is equation number, last equation we have given is equation number 13. If you see the 13 last, so this is, let us call equation number 14. So, equation 14 is the general boundary condition in terms of Lagrangian function. Agree? Now, if I summarize this one, in order to optimize our original problem, where the terminal cost is there and the integral part of term what is called performance index is there, in order to minimize that one and subject to the constraint x dot is equal to f of x comma u of t comma t, then our necessary condition is first this you have to solve it. Once you form Lagrangian function, then you calculate that one or solve this one, and also dl with respect to u is equal to 0. You solve this equation using the boundary condition of that one, and this boundary condition, if both the end point final point, that means time is free, the x of T f is also free, then you have to assume two boundary condition you will get, this equal to 0, this equal to 0, agree. So, this indicates the equation number 11, 12 and 14 need to be solved, 14 need to be solved to obtain the optimal solution, to obtain the optimal u star of t and hence x star of t, because u is the independent variable that will drive the state in a optimal trajectories, and hence x star of t. So, this is what we got it naturally. I repeat once again what is the our problem was here from the very beginning. Just see this one, agree. Okay. Next class we will discuss the what is called that using Hamiltonian function, how we can solve that one problem.